the last lecture, last couple of lectures I think, we saw a design of a traffic light controller. The point I was emphasizing, even though the individual components of the design were all familiar to us from the earlier treatment of combinational sequential logic, the point I was trying to emphasize in that design example was to understand the problem clearly, specifications of the problem, and identify the input output signals required, get a state graph which will satisfy all the requirements, and once you have it, you have standard procedures of implementing or translating these state graphs into hardware. I want to do one more example, emphasize another point, slightly different point here. See, there are two types of designs in the sense, one is the control aspect. In the traffic light control, the control is the most important thing. There is no hardware involved except lights and maybe a timer. So, you can incorporate the signals required for those into your state graph. On the other hand, there may be designs where you may have to design around components that are available. These are called off the shelf components, off the shelf elements. Like you are trying to do a arithmetic logic unit for a computer. You do not go and design arithmetic circuit, subtractor circuit, adder circuit, multiplier circuit, logic circuit, it is all there. You can buy a 4-bit ALU as they call it, arithmetic logic unit, 4-bit ALU or 8-bit ALU, and then control this using the algorithm. I already defined the word algorithm to you, I think more than once. That is a systematic procedure or the sequence through which the circuit has to go through in order to implement the given problem. So, the controller controls the functional blocks in accordance with the specifications of the design, but in order to do that you need to understand what are the signals available from these functional units, what are the signals available for controlling these functional units as inputs, what are the signals available from the functional units as outputs, which can be incorporated into our state graph, because our state graph actually has states, external inputs, external outputs. It is not the state in which this circuit has to exist based on the sequence through which it has to go through to implement a given example. On the other hand, we also have inputs, external inputs. The typical one output example, we have been using X is the input and Z as the output. Circuit exists in several states, X is 0, it goes to this state, X is equal to 1 goes to the other state, and one state Z is 0, the other state Z is 1, and all those things. So, same things will now be delivered given by those functional units which you decide. The 4-bit ALU as an example, what elements control, for example, how do you make a decision, how do you do an addition rather than a subtraction from 4-bit ALU. So, what signal should be given to 4-bit ALU to make an addition possible, what signal should be given to it to make a subtraction possible, and so forth, the logic operation possible. So, input signals of the ALU have to come from your state graph, which are the outputs of the state graph. The Z of the state graph, output of the state graph acts as the input to the functional units. Similarly, the outputs of the functional units, like the operation completed, suppose you are doing addition with a carry, a overflow. If the carry is there, you have to proceed. If the carry is not there, you have to stop, let us say, a simple example. Then I should be able to take this into account and feed into my state graph. Carry as an output of the functional block ALU, but that becomes an input to my state graph. If C is 0, carry is 0, I go to the next state, C is 1, I stop. So, the inputs of the state graph become the outputs, or the not become, are the outputs of the ALUs or the functional units, and inputs of the functional units have to be derived from the state graph, outputs of the state graph. Outputs of the state graph become the input of the functional units, output of the functional unit becomes the input of the state graph. So, I should have a tie up between these two. So, our design is based on the available, because every time when somebody asks you to do a small thing, you cannot go from scratch. Give me 15,000 AND gates, I will start design the circuit and give it to you. You can't say that. You have to work with what is available. We already saw a flavor of that in multiplexer based design, ROM based design, PLA based design and so forth. We have to carry that to a larger circuit like ALUs, 4-bit ALUs, or even I may have a memory unit. Memory unit, how do you put things into memory, how do you read it from the memory, what is this timing signal required, what is the control signal required for reading operation from memory, what is the control signal required for writing operation to the memory, what are the timing signals I have to give, so forth, or anything else for that matter. So, the example that we took earlier, the traffic light controller, did not have many of those features because the functional units there were very simple. The functional units were the lights, and lights did not have anything except to say if you give a signal it glows, if you do not give a signal it does not glow. So, we did not separately treat them as inputs of this function unit going to the state graph, output of the state graph going to the input of the function units. We did not see it that way, we integrated the whole thing into one design. But many times most practical designs, they have to separate out the functional units from the control units. This is an approach, again I have used this word earlier, top down design we call it. We have to have an overview of what we want to do. The calculator chip you are designing, what are the things that are going to be available already to you, around which you are going to design. Of course, finally you will integrate the whole thing and bring out a chip for a calculator. Does not mean that the individual design have to go from gates. Does not mean that individual design have to go from exclusive OR gates for half adder. You can have a 4-bit full adder or 8-bit full adder which is available as an integrated circuit and design it around it, and finally you can integrate the whole thing as another IC. So, the functional unit control unit concept becomes an important part of a digital system design when the system becomes a more involved system than a simple controller like a traffic light controller, elevator controller, or a washing machine control where you have to just detect the level of the water, stop the flow. These things are simple, I can integrate, even there I can functionally partition it. I can functionally partition the traffic light controller. The timer is an external element which is available to me. The timer requires a signal called time on or time start, and timer gives a signal output saying the time is over. So, I can treat this as a functional unit, timer is a functional unit, timing is the input, start timing is the input, end time is output, and this input goes from the state graph and output goes back to the state graph. I can treat it that way, but I do not have to, a simple trivial design I do not do it. When the design becomes complex, a microprocessor, a computer, a microcontroller, and so many other automotive electronics, many features to be controlled, where functional units are defined or available already by somebody else, either they are available as standard commercial components, in which case you call them off the shelf components. What do you mean by off the shelf components? You can go and buy it from an electronic store. Off the shelf they take it and give it to you, this is called off the shelf component. Or somebody might have developed it, it may not be an off the shelf component, but somebody might have developed it for some other application, you do not have to redo the design. You might have done it, your company might have done it for another design, plug it out from that fellow and put it in your design. As long as it is not copyright violation, you can do that. So, this is what I want to teach you, the partitioning, another approach to top down design. Top down design works in two levels. The level we have been talking about is you define the problem, complete overview of the problem, give complete specifications, input output signals, find out what you need, draw the state graph, from state graph we go to implementation. That is a top down, but here I am going one level above that, have an overview of what it is, what are the functional blocks required, which functional units are already available to you, which functional units have to be defined by you, and how are they interconnected in terms of relations of timing and signals, and then try to drive the state graph. So, this is a top down design in its a higher level or a purest form, right. So, what I am going to do is any problem will have a functional unit and control unit. It may be trivial or it may be complex, but it is possible to partition any digital system into a functional unit and a control unit. Control unit is one, functional units may be many. If it is trivial, you do not do all this paraphernalia. If it is non-trivial, you do this paraphernalia, right. So, the function units output have to be monitored before. I can't say, suppose I want to do a multiplication by repeated addition or what is known as the shift and add algorithm. I shift the digit add, that is what we do normally by paper pencil. I can add it, before adding it I should shift it, right. So, why do I need this feedback from functional unit back into the control unit? I cannot start a step in the control without knowing the result of the previous step or without when the previous step is not completed. So, I need the information from the function unit back into my control unit. These signals are called status signals. The status of the functional unit has to be known to the control unit. The one line does not mean only one signal. I am just giving a, in digital parlance, in digital convention, they put a slash. When you put a slash across the line, it means there are many signals. Or they put a thick arrow. You might have seen this in books. A thick arrow will mean several signals, or a signal, the slash. If you know the number, you put the number here. If you do not know, you just leave it. So, several status signals are required by the controller in order to design the next thing to do, right. Likewise, the controller issues, based on this, controller issues the signals which are command to the functional unit. Do it. Now you have finished shifting, now go and add, or you have finished addition, now go and multiply. So, the next step is always given out by the control unit to the function unit. So, this signal naturally should be called what? If this was called status signal, what will be the logical name of this signal? I find the status and give command. I said I give command. Controller gives command based on the status. That means this signal should be called a command signals. But the functional units do not operate on these signals. Functional units are only controlled by these signals, or control signal and command signals, and status signals are the status of it. But they operate on data. I cannot add numbers from the control signal. The numbers have to be fed separately. So, in addition to this, I need to put in data in and data out. So, data in general form, data does not always mean it is numbers. It is a multiplication, it is a data. Addition is a data, storing is a data, or some other operation, it is some signal. Some signal has to be processed, let us say. This functional unit processes data, puts it as output. In that process, it cannot do it arbitrarily at its own will and pleasure. It will do it based at the behest of the control command signal and give the status of the state. So, it is and gives its status periodically back to the control unit, saying that I have done it, so what next should I do? Likewise, I can also have control unit external signals, because starting the whole operation need not come from the function unit. It may not be a status signal. I may have to give an external push, a push button, get started, reset, computer hangs, what do? You push a button, reset button, right. So, sometimes you have to restart, sometimes you have to start with the beginning, sometimes you have to give some external signals which are not related to the functional operation of the functional units. So, in addition to these command signals, status signals inputs and command signals output, this control unit also will have signals called external inputs typically as I said start, and also periodically gives out, suppose the operation is completed, the result is ready, you can go and look at the result. That also can be a function of the control unit. Control unit, in addition to giving the commands, can also give out signals to the external world saying that the operation is completed, or hanging, error, I cannot proceed because this data is missing or incompatible, whatever you want to display. It may not be the result, but the some sort of an output for you to know what is happening. So, in addition to control, similar to the external inputs, you can also have external outputs. This is a generalized model of a top down design of a digital system. Now, within this there is no rigidity in this partitioning. A timer could be outside, a timer could be inside. If you can count every clock in a control loop, then the timer can be inside my control unit. Or if you put an external counter to count my time, it will be a functional block which can count. So, there is no rigidity in the partitioning, because there are certain things that are specifically functional unit, like an ALU, as I said as an example. I cannot think of ALU as a part of a control unit, but if you want to, you can always do it, but you can push in things into this or from here to here. So, partitioning is not a rigid partitioning, it is a, what shall I say, this is a soft partition, you can move things around, like those, some of those modules they put in office space nowadays, they just remove, and then in conference halls you might have seen this. There is an open session, everybody will be there, and then they will remove all the in between partitions, and then suddenly they will break into 3 different sessions. Suddenly wall will come up when you have gone out for tea. When you come back, it will be 3 different rooms. You might have seen this, I don't know. When you start attending conferences, you will. Right, okay. Now, function unit, and then now what we have been doing till now is, of course, function units separately we studied many functional units in this course, counters, shift registers, we did arithmetic unit, I mean adder, subtractor, we did even multiplier, I think. A multiplier example I remember doing, and we have done other things, code converters, things like that. Control unit, what we have been studying on the sequential circuit design, state description of a problem, implementation of state. And if there is no specific function units as required thing, we put into this control unit everything. We did not call it at that time control unit, we call it the full design, because the system is such a simple design. We did not partition into control unit, and that is what the extreme of this partitioning, soft partitioning. The entire control unit can be gobbled up, I mean entire function unit can be gobbled up by the control unit. Of course, the reverse is not true. As long as it's a sequential machine, it has to go through states, and states are represented in the control units. So, we have been concentrating this, and the examples we did last time. The example we did last time concentrated only on this. There are external inputs with the timer signals, external outputs with the lights. There is no command or no status because there is no function units. So, we use these internal inputs, and then the states were defined in this, and it went through different states. And this further has to be very clearly specified, everything has to be clearly specified. If you are vague, your design will be vague, and if your design is vague, it does not work properly, and if it does not work properly, you are not satisfied, malfunctions. How critical it is depends on the operation. Supposing it is some TV remote which does not work, you do not worry, all you have to do is to get up from your sofa and then go and do it manually, but then if a traffic light fails, there is a chaos, and if a flight control fails, you know what the result is. So, these are all different things, the level of criticality. So, everything has to be defined clearly. Once a problem is given to you, you should know whether there are enough or known functional units which can implement this, list them out. And after listing them out, to find out what is the input requirement of each one of this and what are the outputs available from each one of this. Inputs of these have to come from here, outputs of this have to go back into this. In addition to, this is addition to data. Data input, data output is independent. Supposing I have a adder, the data has to be there. 4-bit adder means there should be 2 4-bit numbers, result will be a 4-bit number with a carry 5-bit number. In addition to that, is there any start signal available? Is there an enable signal available? Is there an end of addition available? So, each functional unit you should list down the control signals available as outputs and control signal required as inputs. When does it start? For example, take a shift register, load is a control signal, clear is a control signal. These are things you should list out, and then based on that you go to the start your sequence. Available signals and available required available functional units and required signals are listed. Based on that you start your state graph. What you have been doing till now is to ignore the first part, because we have been taking very simple components or standard components and we were only starting with the state graph. I am now taking you one level up, that is all. See, there is no contradiction in what I am saying. So, we can do a simple design of a counter. The counter is available, what is there to design? You can buy it and do it. Otherwise, you can get flip flops and connect them together like that. That is what I am saying. At different levels you have to go on, because finally today's digital world is so complex in terms of its number of functional units and the complexity of control. Functionally they have not become very complex. Whether it is a Pentium processor or a simple calculator or a 8085 microprocessor, addition is addition. Maybe there are some techniques which make the addition a little faster in Pentium processor compared to the olden days. Complexity does not come in the functions, complexity comes in the control aspect, because so many things are there to be controlled at the same time and timing have to be very strictly maintained. So, after understanding the problem clearly, partition the problem into functional units and the control unit. Functional unit, you list them, see whether they are available, and if they are available, what are the data input, data output requirement, plus what are the control input, status output available, control input requirement, status output available, and start your control unit by means of a state graph. So, our state graph implementation of the digital circuits, we have been systems or subsystems we have been discussing so far is only this part. Because of the soft partitioning, some of these things we have been able to push, like the traffic light controller part, the light was inside this, and some other things we did earlier, sequence detector, if you remember, if we did some, those things we did not talk like this, we just put it all together. So, this comes the same way, there is no change in that procedure. I have to draw a systematic state graph starting with the various sequence of events that the circuit has to go through. In the case of traffic light controller, we said the sequence of lights it has to go through, we drew diagrams to illustrate them, and then drew the state graph. From the state graph, every time the state graph, your compatibility must be maintained between the function unit and the state graph. Any input required in the state graph has to be available as a status signal from the function unit, and any output coming out of the state graph should be able to go as a command signal into the function unit. That compatibility has been maintained when you draw the state graph. Sometimes it may not happen. Once you assume that something is possible, it requires an extra signal, control signal. You do not have it, how do you do it? You modify your function units requirement. Where function unit is an open world, it is the electronic shop, as I said, you go and buy. If it is something that does not suit you, you throw it out and buy something else. I will give you a simple example. Supposing I say add, shift and add I said as an example of multiplier. I give a shift signal, you can shift, a shift register, add. We have seen 4-bit adders or 1-bit adder we saw, in fact we also saw half adder. In a 4-bit adder we give 4 inputs, 4 bit input for A, 4 bit input for B, get sum 4 bits and carry 1 bit, 5 bit output. As soon as A and B were given, sum was available based on the timing delay of the full adder. Is there any control signal as input which says add into an adder? Did we see that when we drew the full adder using exclusive OR gates and all those things, even carry liquid adder we did. A and B and full adder is a combination circuit. I have been maintaining this, right? It is not a sequential circuit, unless it is a serial adder, 1 bit adder, which we are not talking about here. We are talking about parallel adders. When you say 4 bit full adder, you mean 4 bits are given as A, as 4 bits are given as B, and sum 4 bits and carry 1 bit comes 5 bit comes output, assuming ideal components immediately, practical components after delay depending on the gate structure. Is that right? Now, supposing a control signal says add and shift, and controls add comes from the controller. When I draw the state graph for multiplier, I will say shift and add, shift and add algorithm it is. So, shifting no problem, there is a shift control in a shift register. If it is not given, it will not shift. Whereas an add, in adder 4 bit adder, is there a control called add? Tell me. So, how do I use this signal? Sometimes, how do you use this control? How do I control my adder? How do I control the adder when I want to add? As long as input A and B are there, output is there immediately, and we are talking about here clocks which are slower, and those combinational delays are very small, nanoseconds delays, correct? Combinational delays are nanoseconds, whereas clocks depending on the frequency operation will be much larger periods. So, it is not going to wait for you to give an add signal. As soon as A and B are given, it is going to give an output. So, now I want to control it when I want to add. I can only add after shift or shift after add, whatever. So, some sort of a control is required. Then I think, okay, maybe a 4 bit full adder is all right, but something else has to be there. So, 4 bit adder can feed into a register, the output register can be controlled. I can load it when I want to add it. Do you understand what I am saying? Supposing I have a 4 bit full adder. Please understand what I am saying. Now, this is A, this is B, and this gives me C or sum, and this way carry. Now, there is no other control in this except power supply and ground. Now, I have a coming out from the command signal controller called add. This has to go into this. Only when this comes, this should add these two numbers, otherwise it should not. No possible, it is not possible. I can't just control somebody, it is combination logic. The moment I give the thing, the output comes, how can I control it not? So, what I do is, as a simple solution, I put a register. After all, this can go into a register, adder, output can go into register. How many bits? 5 bits, because this 4 plus 1, 5 bits. So, you get a 5 bit register, and the register will have a load signal, and I will give this command into this load signal. So, even though I am having an illusion of controlling the adding, I am not controlling the adding, I am controlling the loading of the adding. The result is available when at my request, at my command. At the controller's command, the adder result is available. Adding must have happened earlier, but I am not going to use it. I will look at it, okay, you do what you want, but I will look at you only when I am free. That is what the controller says to the full adder. They do not speak anyway, I am just, right. Okay. Why am I saying this? So, when I draw the controller state graph, some of these nitty-gritties have to be sorted out. So, you cannot simply blindly put a signal, command signal add, command signal control, command signal shift, and you have a full adder. You go and buy the full adder from the market and come and there is a hanging signal. You have wired up this part, you have wired up that part. There is a command add command, add command. You do not know where to insert it into your breadboard. You should have thought of it in the beginning. So, I looked at the So that is what I say, when you look at the functional unit, in addition to data input, data output, I list out all the control signal requirement and the command signal output, status signal outputs available. So I will see that there is a missing command signal, so missing signal called add. So you go around asking the entire electronics market, do you have a signal adder which will add, maybe there is one with an enable, something like that, you buy it. Otherwise your solution is simple, get one more register in addition to adder and get the result into the adder, of the result of the adder into the register and control it. And nitty-gritties like this have to be sorted out when you draw the control unit, and functional unit minor changes. So you cannot run one more time to the electronic store, so you have to finish it before coming out of the inventory list. Likewise in the command signal also, sometimes you try to accommodate everything, it is not possible, then I change my control a little bit. Okay, you tell the customer this is not possible, I can do it this way if you want. You will say yes or no, and if you say yes, proceed. So I may have to modify my control unit and the functional unit slightly, fine tune it, trim it based on the availability of the functional units, based on the requirement of the controller. Once I am done, rest is easy. I do not have to teach you how to do a functional unit, there is a command unit, as a control unit, as a state graph. Once that stage is completed, it is sealed. From then on it is a state graph, transition table, flip flops or multiplexer base, ROM base, PLA base. Again and again I am emphasizing this fact. I might have told you this 100 million times in this course. Design is the most important part of digital. No? Putting it together, of course you should know what is available, you should know how to do the most efficiently, most reliable component, you should know where the power supply should be given, but what is the most important part of an engineer's job? Design it properly so that it is reliable and it works to the exact specifications given to you, because we do not know how critical the application is. You can't be vague about it. If it is vague, you ask for details, and if something cannot be accommodated, go and say this is not accommodated, what else do you want in this place, and you give the alternatives. Don't go to the customer and say I can't do it, tell me some other way of doing it. No, you are supposed to give the alternatives. I can do it this way, this way, this way, choose, but not this way you want. These are the other three alternatives, choose one of them. So this is how a full real digital system design is done. So this will be the last example in this course. I am going to take a simple example to illustrate this concept. The example is so simple, it is not going to take much time. But I wanted to introduce this major concept. You see, finally I wanted to go from a gate, definition of a gate and reduction of gates through various Boolean algebra, corner map, combinational design, flip flop, sequencer design, and then the MSI component, LSI component, the state graphs. Through the system design, some of the systems we did, but I thought this would be the, I will have to go to this level, it's a logical completion of this course. So I will have to take one more example which will illustrate this point. Let us define this. It's a very simple example, as I said. Again, I cannot design a microprocessor or a calculator. I cannot design a what shall I say, computer in a class like this, but it's beginning of these things. The example is a very typical example. I have a register. See, many times you want to do some operation, manipulation. You want to find the number of ones, odd bit, even bit. We talked about parity, remember, long ago. Parity is what? The number of ones in a bit stream is odd or even. Is odd, is called odd parity, is even, is called even parity. No? So suppose I want to design a parity generator. Before that I need to do some counting of number of ones. Suppose I have a bit stream and I just want to do a simple job of counting the number of ones in that bit sequence. That is all I need to do. This will become a part of a bigger unit, because I am designing a computer in which several things are there, and a small local unit is a circuit to count the number of ones in a particular register. So I have a register called A. The problem is to count the number of ones in the data, in the 8-bit data, or not even necessarily 8-bit now, the data stored in register A and store the result, that is how many ones are there in a register B. Very simple job. I have two registers, a register A and a register B. Some data which is available, I will first have to store it in register A, count the number of ones in that data, and then put that number the number is the number of ones in another register called register B. That is all. I can't possibly do it without functional unit partitioning, but may be difficult. But functional unit partition makes the problem so simple. Just to give you an example, I thought of this very simple, not picture on this problem as a simple problem for you to understand the concept of partitioning between functional units. So, functional units, what are the functional units here? Register A and register B. We should also know the control signals required for function A and function B and the output signals available from. Then I will have to do a state graph of the sequence of events, how to load the thing, how am I going to count it, and when the result comes, how am I going to write it into the register B. All that has to be put in the part of a control unit state graph. Once the control unit state graph is there, I will have to implement it using multiplexer based solution, whatever is the most favorite solution of yours, right. So, first part is, as I said, the functional units. So, I will call this register A and register B. It is not complete. Functional unit has to completely define these registers. Number of bits, command signals, control signals required for this to operate, and status signals that can come out as the register as the output can be used in my state graph. So, number of bits I do not know, since the problem did not specify the number of bits to be stored, that will be assumed that the customer will tell you that. So, if it is an 8-bit register, you will use 8 bits data to be stored, you get an 8-bit register, 16-bit data to be stored, put a 16-bit. So, now I will use n bits in data n. So, the n bits are available also. So, I need a parallel in parallel out register which can hold n bits, where n will be defined by the customer client, right. And what should be the size of this register B? There are n bits. How many ones can be there? N ones. So, the n bit register, so that can be how many? What is the size of? Say it again. Logarithm? Huh? Log of n base 2. So, the size of this should be okay. Oh, n bit, all, yeah, log of plus 1. Supposing it is 8 bits, all the 8 are 1s, 1 0 0 0, no? 4. I need 1 extra bit. So, if there are 8 bit number, all the 8 are 1s, I will have to store how much? 8. 8 is what? 1 0 0 0. So, I need a 4 bit register. If it is 7, only 3 bit register. So, it is log of n plus 1. This also input and output. course this need not be put there, I am just saying the size of this. This also can be a parallel, but we do not need it, because it is going to increment by. So, the size of this would be, this output is required, log of n, because I need to use this in my next step of my computation, So, this should be parallel in and parallel out, this should be parallel out, parallel in is not required, where I am going to count it. But then register B should have, now we will complete the requirements of A and B completely. Now look at A. A is a register which will store the data, so it should have a loading feature, right, so load feature should be clocked, because only then it will load and clock. I will assume all of them are synchronous operation to avoid confusion. Loading, clearing, all the operations will make it synchronous. You know what I mean by synchronous? Along with the next clock edge. As soon as signal is given, it does not do the job, it waits for the next clock edge and does the job. So load is synchronous loading, that means when I want to load a new value, I put the value here and put one load on one and clock it, next time it goes. Is there any other signal required there? Now we have to decide how we are going to do that. So algorithm has to be decided. How am I going to find out the number of ones in a bit stream? In a n bit register or 8 bit register or 8 bits of data that is stored in register A, how am I going to find out how many ones are there? I can do it so many ways. I can add the bits, do what? What I can do is to look at one bit at a time and keep shifting it. So I will always look at the LSB, the least significant bit. If it is 1, I will add 1 to the register B and then shift it, because algorithm must be simple. I can think of so many other ways of doing it, but simplest way I can think of is, or one of the simplest ways I can think of is, look at the last bit LSB, if it is a 1, add 1 to my B register, shift it by 1 bit, again look at it and then keep a count till n is over. When n is over, stop the process. That is going to be my control algorithm. The state graph will be decided by that. So I have a rough idea what I am going to do. I will go back, I will assume this, go start my control algorithm, and if there is any problem I will come back and correct it required. As I said, fine tuning, back and forth going couple of times to trim the requirements. So right now I am going to say a shifting feature is required, and I want to shift left, shift right, so that LSB will always be. So I will say shift right. So my requirement of register A is a shift register, n bit shift register, loading feature, shift right feature, and a clock. And register B should be again clocked, because whatever you want to do. I will use as a counter. I will clear the counter to start with. So I am going to use it as a counter. Will be a counter which will be cleared, and every time there is a 1 in the shift register, I will count it. So I need a signal to count enable. That is all. So as of now I am defining 2 registers with architecture functional units. One register should be a shift register in which I will load the number, look at the LSB, if it is a 1 I will add 1 to the register B, if it is not I will shift it and again look at it and keep doing it till all the bits are covered. How I am going to do that, we have to think about it. It will all come in the algorithm. But now the first cut the first cut requirement I have to give now. So these are the specifications I am giving. I may have to change it a little bit. So right now I am saying a register which has a shifting possibility and loading possibility, whose data in and data out available is what I need for A. For B, I need a counter which can be cleared to start with and enabled whenever we want at the edge of a clock, and then output should be read parallel out. Finally, the result will be out. How am I going to use it? I will start my state graph, and then when the signals, nitty-gritties of the signals are available, if something is not available, I have to go back and make a little modification of this. But so far whatever assumed is available in the market is off the shelf. I can buy a shift which is a loading feature and shifting feature, or I can buy a counter which can be clearing feature and a count up feature. So I have not violated any norm and common. Even if it is still worth it, because as I said, the similar requirement somebody might have done it earlier, and design is available with you in your company and can use it later on. So we will continue this discussion and complete the problem.